Good morning. My name is George Murgel. I'm a senior environmental engineer with HECO Engineers. Here today to give a presentation about water reuse as a water management strategy for wastewater systems. Wastewater reuse has a lot of different connotations over time. The current U.S. Environmental Protection Agency definition is referring to using wastewater or some type of reclaimed water for one application in some other application. And in this context, what we're typically going to be looking at is municipal wastewater being used for some other activity. The idea of water reuse has a number of different definitions and a number of different activities. The U.S. Environmental Protection Agency, EPA, definition for wastewater reuse is using wastewater or reclaimed water from one application in another application. In this context, we're going to be typically referring to municipal wastewater or sewage as the material is being reclaimed and reused. The activities for water reuse have a number of different categories, as you can see in this diagram. Treatment, there's the concept of health and public welfare that is involved, regulations have to be followed, and economic capabilities as well. To understand the concept of water reuse with wastewater, we have to really look at the historical perspective. The genesis of water reuse began with the water resources management capabilities. Now, water resources management many decades ago dealt primarily with control of water. This was the utilization of water for different activities like water supply, irrigation, power generation, and so on. And water quality control was one of the aspects that had to be dealt with. Now, when you look at and think about water resources management, one of your key components is looking at water supply, the chief subsystem. You've got groundwater wells that can feed into treatment, that can feed into your distribution system. You've got natural sources of runoff from watersheds to reservoirs, feed into treatment, feed into your distribution system. And in both cases, what you end up getting out of that is a collection of wastewater. And the wastewater would go through some type of treatment and then would have to be disposed of. Oftentimes the production in your water supply system is based upon your demands, what municipal demands you have in terms of your residents, in terms of your businesses, in terms of your industries. And all of this gets tied back to the water cycle for the earth and all of its interactions. When you look at the water cycle, we know 3/4 of the earth's surface is covered by water. However, when you really look at it, only a small fraction is available for all of humanity to use. In that context, you've got groundwater, which is only about 0.63%. You've got lakes and streams, which are an even smaller fraction at 0.016%. And so when you add those two together, out of all the other possibilities, you've only got a little under 0.65% of all the water that is on the earth that is typically available for humanity to use. Groundwater, typically we're looking at only down to a depth of about 4,000 meters. Those are some of the deepest production wells that have ever been drilled. Really, to go much deeper than that is very difficult. There have been some test wells that have gone down much deeper, but typically they don't yield any additional quantities of water. The amount of water that gets used is typically going to be controlled by what the demands are. The particular influences that we have on those waters in kind of a rank order relate to industrial activity, how well the water that is used is metered, what kind of management we have of the overall system, and the standard of living as well as climate. In these days when they talk about climate change, how the distribution of water occurs across the Earth's surface can get into some issues of how much water is actually available. When you look at this cycle, you've got water coming down to the Earth's surface, eventually getting to the oceans, eventually getting back into the atmosphere where it can precipitate back down onto the surface. In the early years, the amount of water that was available, that didn't seem like it would be much of a problem. These days, with population growth, current population in neighborhood of 7 billion around the planet, all going and trying to access the same pool of available water, there's less water available for each person to be able to access. When you think about the use of water over time, some of the earliest activities using water occurred back in the neighborhood of 3000 BC. where you had different rainwater, sand filtration, where they tried to collect different amounts of precipitation to be able to reuse for whatever use they deemed necessary. As time has gone on, you've got the advent of agricultural irrigation projects from the 1890s forward. You've got different industrial uses that began to grow larger and larger in the 1920s onward. And you get then up to a more current time frame in the 1990s and the early 2000s, where you have the EPA and agencies for international development looking at guidelines for water reuse. And in that context, not only just reusing the collected water from basically precipitation, but now beginning to think about what other sources of water can we press back into service, because the existing sources are beginning to become scarce. You got many more people trying to access the same quantity of water, meaning less per person in that context. When you think about the water resources management then, certainly traditional approaches were modifying water storage and flow patterns using dams and reservoirs or interbasin transfers. California is a good example where you've got water sources in Northern California being directed south toward Los Angeles in that area to be able to meet the demands for water. Wastewater disposal is one aspect of beneficial use of the water supply. It is a resource that up until the last few decades, the primary goal of having that wastewater, you treat it and you try and get rid of it somehow. In a lot of areas, the given adage was out of sight, out of mind. So you would treat it, you would try and get rid of it in some way such that you didn't have to worry about it any longer. Over time, of course, that has led to a lot of different problems that have occurred. Thinking of the wastewater disposal, we've got worry about the volumes. The volumes, however, are not well measured. Unlike the drinking water that you would get into your home, which is typically metered, you will find out that wastewater is seldom metered in any way, shape, or form, except at the treatment facility. The key that we have to think about dealing with wastewater disposal is that the goal is to protect public health and prevent it becoming a nuisance. Finding a cost-effective solution, finding some way to dispose of that water is one of the issues of concern. EPA then, when it was originally set up back in 1972, had or was given the task or the goal of trying to set the standards and enforce the cleanup of this wastewater pollution. Back at that time frame, you had many rivers, bodies of water, which had become so polluted with wastewater disposals of all types that in some cases you could literally walk across the river because it was so contaminated. You had rivers which actually caught on fire as a consequence of the wastewater pollution. So EPA was given that goal of trying to set up a way to handle that wastewater and prevent that nuisance, prevent the degradation of public health as a consequence. In our area, the EPA is basically 10 regions. Region 10 encompasses Washington, Oregon, and Idaho, which would be the region that would primarily deal with the state of Oregon. Historical regulations have been meant as guidance in terms of how you operate your water and wastewater facilities. The demands that have occurred over time have meant that the standards for treatment have continued to increase, so they're ever more stringent. The growth has been the chief threat to water quality and availability. Almost all areas have not been immune to this growth pattern, and so the ever-growing demand from the water sources means that there's less and less available to go around. The stringency of the regulations has been ever increasing. The ability to direct discharge that water is essentially gone away. That opens up the door for looking at other possibilities of what you can do with that wastewater when it's time to get rid of it. The impacts of a lot of the development and economic concerns have led or have been driven by water shortages. Many of the arid areas of the U.S., this is becoming more and more of a problem. There was one point in time around the country where a good portion of the country could be considered as having drought conditions. Even today, we've had, some years have been very good in terms of precipitation, some have been not so good. There are still areas of this country which have essentially declining quantities of available water from the hydrologic cycle. In order to maintain what we have in our ecosystem, we have to think about that depletion of water resources and what other sources of water might we be able to tap into. From the context of the hydrologic cycle, we know that technically speaking, yeah, you've got glaciers, you've got the Antarctic and Arctic ice packs, maybe those would be a source of fresh water. There are a lot of other logistical issues. I mean, there have been studies done about trying to see what it would take and how much it would cost to take an iceberg from the Antarctic ice shelf, tow it up off Los Angeles, let it melt, collect that fresh water, and put it into the system. Nothing has ever occurred in the context, it was just a paper study. But that being said, the demands for water are still ever increasing. Being able to identify additional sources has become a recurring goal. When you look at what this means for Oregon, parts of Oregon, as you can see here, are very arid. Yes, you've got the Cascades, Pacific Coast area. The blues and purples and greens are very high water precipitation amounts. Over half of the state to the east of that area typically is going to be in the rain shadow from the Olympic Mountain Range. Water there is relatively scarce, primarily going to be from groundwater. So when you have a drought year, the amount of available water decreases tremendously. This has occurred in the past, the trend could continue to occur into the future. Being able to find a new source of water, especially in these arid areas, becomes very critical. In all situations, water rights are going to come into play if the droughts continue. Most often, water that is used for domestic purposes, we'll see about 70% of it ending up in a waste treatment process. And for the most part, in the past, that 70% of what was used for domestic purposes was no longer available. It was disposed of in such a fashion that it left the water cycle, so to speak. When we're treating effluent and releasing it into a nearby water body, it's typically no longer available for reuse. What does get released into that water body, of course, when you have a number of different municipalities along a stream or a river, what becomes one town's wastewater is going to be the next town downstream's drinking water. A good example of that is the classic Budweiser story. Back in the 60s, 70s, maybe the 80s, in St. Louis, the Budweiser brewery is located right on the banks of the Mississippi River. The city of Chicago releases, at that particular time, is around 10 million gallons per day of effluent that they treated, the wastewater, and dumped it into the Illinois River. Well, the Illinois River dumps into the Mississippi River, well upstream of St. Louis, and so those two mix and they move on down toward the Gulf. Well, the Budweiser brewery drew all of their water for their processing from the Mississippi River. Yes, they treated it before they used it in their process, but the flow at that point is about 100 million gallons a day. So at that point in time, you could think of 10% of the flow is treated Chicago effluent. So 1/10 of your can of Bud is treated Chicago effluent. Very good example of how that one municipality's waste is another municipality's resource. What that has led people to start to think about in the context of water reuse is how can that wastewater treatment volume that gets dispersed into rivers, some into groundwater injection, how do we deal with that in terms of using it for some other purpose? Well, that leads us to the concept of sustainable development. And in this particular situation, what we're thinking of is a new way to interact with the environment such that the development and the water that is utilized can end up going together hand in hand. What we're trying to do is meet the needs of the present without compromising the ability of future generations to meet their own needs. And in that context, what we're looking at is predicting how changes in climate will affect the hydrologic cycles and will allow us then to tap into that wastewater resource as a way to try and mitigate these changes or impacts that are going to be occurring. The reuse rationale that we're looking at is thinking about water sustainability by using it efficiently. We know it's a limited resource. We know recycling is already happening and it's becoming more and more prevalent as time goes on. But what that will end up allowing us to do is also become more efficient in the use of the energy. Oftentimes when we think about wastewater, of course, the quality of treatment has to be appropriate. There are a number of non-potable uses like irrigation, industrial cooling that can reuse this wastewater. The level of treatment does not necessarily have to be as great as if you were going to try and reuse this for a potable water source. Now that has been looked at. Technically speaking, it is possible, but there are a number of other issues that will probably prevent that from happening anytime real soon. Having the wastewater reuse criteria allows us to protect the environment in general by reducing the volume of water that gets sent back to these receiving waters. As we've said, the treatment standards are increasingly more stringent, so the level of quality of that water becomes greater and greater over time. If we can make use of the wastewater, what that's going to help us to do is to conserve our freshwater supplies. Instead of spreading a limited quantity across many uses, we'll be able to reduce the number of uses that will tap into the freshwater supply because we have this other source of water which isn't necessary for drinking water that we can use for irrigation, for other sorts of activities. And in the urban environment, this becomes very important when you think about smaller municipalities where your water source is used not only for drinking water, it's used for irrigation of lawns, your shrubberies, your parks, golf courses, whatever. If you can take that source of water and reuse it with a different activity, then you have the potential for less environmental degradation. Look at a zero discharge facility. That would be one which is taking all of its wastewater, is not discharging it to the environment, is able to completely reuse it in some fashion, which means that the regulatory oversight is lower, there's a more consistent regulation that will occur over time, and the level of stringency will not increase nearly as much as it would if you were trying to dispose of it into a water body. The reuse also has some economic advantages. Certainly it will have reduced economics in terms of needing supplemental sources. That water, the wastewater, will have some nutrients, typically some nitrogen compounds, it'll have phosphorus as a consequence of becoming a wastewater, and those nutrients can be useful for irrigation of crops. The reduced nutrient loads that would be sent to streams, if you still do have a final disposal, means that the streams will improve their quality, and that will both help the fish and the tourism industries as a consequence. Now, there's a number of factors that will drive the implementation of a wastewater reuse program. Typically, the proximity in the urban environment is going to be a key factor. Oftentimes, it is going to be the area where it is most needed, and it will likely have the highest price in order to be able to implement it. Rural areas, it's not as big of an issue because you have a lot more land, a lot more ground that is available. How dependable is your resource? Certainly in drought years, urban wastewater production is going to be relatively constant. So you have a source that can be reused at nearly a constant level without regard to whether it's a drought year or a precipitation year. Is the system versatile? What kind of technically and economically proven processes are available that can be used to treat the water to get it to a level that it can be reused? Non-potable reuse systems also we look at in terms of safety. Over the past 4 decades, wastewater reuse has become increasingly more likely, and in that time frame there has been virtually no adverse public health effects as a consequence. You're removing competition in terms of water resources by taking that wastewater as now a resource and using it for activities that primarily would have made a draw or a demand on those water resources. It's oftentimes fiscally responsible. There's a lot of public interest that is being generated over in recent years in trying to take what was a out of sight, out of mind type of activity and bringing it into the mainstream so it becomes something that can benefit a number of activities. It has a proven track record. Over the past 4 decades, more and more systems have gone to looking at using these types of systems in order to be able to supplement what demands they have. Some of the typical applications, of course, urban reuse. It can be used for irrigation, public parks, schoolyards, highways, residential landscapes, putting less of a demand on your other wells and types of systems. Agricultural reuse would be a very good source for non-food crops, commercial nurseries, pasture lands, grains, that sort of thing. It has been at times imported into recreational impoundments. The level, of course, of treatment and the quality that's necessary is much greater, but it could go for those purposes. It can be used as a process or makeup water, cooling tower waters for an industrial situation. It has been used in the environment as creating artificial wetlands or enhancing other natural wetlands to make sure that you have a continuous flow. There is the possibility of a potable water reuse. While it is practical at this point in time, it is not something that is widely used. There's still a certain disfavor amongst the general population in terms of really thinking about what that water may have been at one point in time. The ick factor, if you will. In terms of water reuse projects, what this does for the capabilities as non-potable application with landscapes, irrigation, industrial uses. An example I can give is I live in Kuna, Idaho. When I moved there in 1996, the town was very small at that point in time, but even with only about 3,000 residents, they were looking at their existing well systems being almost overtapped. They had a very large storage tank, but they couldn't keep up with the demands for irrigation for domestic use. And since that time, the population has grown almost tenfold. What the city, in their wisdom, was able to do was to take and look at converting or creating a secondary non-potable source which could be used solely for irrigation for all new development. Over time, they've actually gone back and are retrofitting some of the existing original town, but all new growth in that area has their own irrigation system as well as their drinking water system. And so they've been able to actually do some limited reuse of the wastewater from their treatment plant, but they have some shallow wells they have drilled into the subsurface, which taps a water source which is not suitable for drinking water, but is eminently suitable for reuse in crops and irrigation. By doing that, they actually were able to reduce their demand on their drinking water source so that it was almost 2.5 decades later, and they have not had to expand their drinking water system at all. So by going to this reuse system, they essentially have expanded the ability to be able to use that drinking water source for that particular demand. Oregon has its own water reuse policy. Every state pretty much does, but in the case of Oregon, it's spelled out in the Oregon Administrative Code, Chapter 340, Division 55, Section 7, which specifically says that it's the policy of the Environmental Quality Commission to encourage the use of reclaimed waters for beneficial purposes, using methods that assure the health of Oregonians and the environment of the state are protected. Specific rules are set out in that particular division as well, describing what reclaimed water may be used for, how you essentially go about getting that process set up. There are specific websites, the Municipal Water Reuse Program description given at this particular location, and then you've got the website for the Water Reuse Program, and then the water reuse information, specific details, including the table of beneficial uses that's on the DEQ websites. So these three locations essentially give you all the information that you need in order to be able to investigate and to look up setting up a wastewater reuse program if you don't already have one. So what would be the next steps? First of all, you have to decide that yes, we need to implement a wastewater reuse program. It would be a benefit, so now we want to move forward. Once you've got that decision made, then what you need to do is the following components. You have to look at and investigate what you need for permits, what kind of guidance and blessing the environmental regulators are going to give you in order to be able to set up the program. Then you have to design or implement an appropriate system for either collection and or treatment, and how you get it to where you intend to reuse it. If you're looking at sending it to irrigation for farming or agriculture, does that mean you need to have a separate pipeline? Depending on the volumes, do you haul it with trucks, tankers? Just how do you go about getting it to where you need to use it? And then you have to keep the public exposed and informed about what you are trying to do. You want the public to have buy-in to the decision to proceed forward. If the public is not interested or doesn't want to pursue this avenue, they can make it very difficult for you to proceed. So keeping the general public informed is going to be paramount. Now, there are a number of specified rules for the recycled water reuse. A lot of the reclaimed water can be used for irrigation and does not necessarily require a water use permit if you have a number of conditions that are met. The Department of Environmental Quality, as I mentioned, oversees the reuse programs in Oregon, and they would require that their particular treatment facility have some kind of either Water Pollution Control Federation or an NPDES discharge permit already in hand. And then except for the water authorized by permit, they would require a reuse plan be developed. And this would then tell exactly how the water plant is going to be set up, how the treatment plant operator will comply with all the rules that are in the regulations. And then the Oregon Health Service would approve the reuse plan, and then it can be either used directly or it could be blended with clean water if you need a larger volume. Water used on a property not belonging to the treatment plant requires a legally enforceable contract. So if you have a volume of wastewater that you want to disperse to some agricultural land, the owner of that land would essentially have to sign a contract to be able to accept it. Reuse of this water for feedlots and dairies, the rules are a little bit different. You would need to investigate them if those were the particular source that you were going to have the wastewater reuse set up. The reuse management plan that would need to be created, of course, is going to have a number of components. You're looking at, of course, describing the facility, what are the sources, what are your flows, what volumes are we dealing with. What is the treatment process that you have, right from the beginning through, initial primary treatment, your secondary treatment, what kind of disinfection you have to get rid of pathogens and harmful bacteria in the effluent, and what are the overall characteristics. This would be both physical, chemical, and biological. What is essentially the quality for the biological oxygen demand, for your ammonia, for your phosphorus, for the solids that would be left in that water that would have gone into the disposal. Do you have a climate such that you need to worry about wintertime storage? If you were in a southern climate, you could probably be able to disperse this for irrigation, for agriculture year-round. Northern climates, such as we might have in Region 10 EPA, we might have a few months out of the wintertime where we would not be able to disperse that liquid. So we would have to have a volume of storage that we could collect it when we can't disperse it and then spread it out over the intervening time that we can, so that we would essentially use up all of the amount stored by the beginning of the next winter season. You have to have contingencies. What happens if you have a spill? What happens if you get some new company coming in that decides they could utilize that water? What are you going to do if they request that water? How are you going to handle it? There's reporting records requirements that would be set up. And what is the overall intended use of the program? And in this particular case, what that's implying is, where are you going to reuse it? What are the sites? You would have some initially that obviously you could use. You need to detail those, including things about the topography, the climate, any microclimate issues for that particular site. What might be limiting factors? What kind of surface and groundwater conditions do you have? What's the nature of the properties around the site that might be using this treated wastewater? And then you have to look at what some of your access restrictions might be. Depending on the type of agriculture, you may not be able to go into that field for a certain period of time once it's been inserted. The level of treatment, for example, if you're going to use it on a golf course, you can only apply it at certain times, essentially when there's no people on the course. So that would be a nighttime disposal as opposed to when you have golfers there in the daytime. In that management plan, then you would also have to talk about the application rate. And of course, for agriculture, that would be a key factor. What crop will it be applying to? what quantity of water does it need, what nutrients are in the water, and what might the plants need. Would you end up needing to supplement it? And in some areas of the country, what would be the salinity of the water? A lot of times if you have sources of groundwater, it might have a high dissolved solids concentration, and so that in turn will carry over into the wastewater such that you end up adding salts to your soils. And over time, if that builds up sufficiently, you either have to change the type of crops that you're dealing with, or the crops will have to be kind of a salt tolerant variety in order to be able to make it work. Certainly for the irrigation system, how do you intend to get it there? How do you intend to disperse it? Is it going to be through a sprinkler type system? Is it going to be through row and furrow type application? And how do you deal with the crops that get developed on those fields as a consequence? Typically, the requirements will include that there's no bypassing of untreated water. You need to have alarm devices and backup generators to be able to ensure that the water gets sent where it needs to go. You've got to have excess capacity so that you can prevent any discharge back into the environment that is not already part of your reuse plan. This doesn't confer any water rights. That's one of the things, as we mentioned, water rights are a concern with getting sources for potable water. In this particular case, there's no water rights that would be conferred. There's annual reporting requirements, and there's also the requirement to keep consumers informed in terms of what's happened. What this means in terms of the level of treatment, Oregon has 4 different treatment levels, labeled 1 through 4, with 4 being the highest level of treatment and suitable for use in any agricultural, urban, or irrigation, commercial, or industrial type of scenario. Level 1 essentially could not be reused in any way, shape, or form, and at a minimum you need to have at least a level 2, which receives biological treatment and disinfection before you can use it even for some agricultural types of uses. So depending on what type of reuse you have in mind, that's going to dictate to a certain extent what level of treatment your wastewater needs to undergo. In terms of the engineering aspects of your particular reuse project, you've got to look at what water quality level is needed. Of course, this will get back in terms of the level of treatment that it has to undergo, how the water is going to be reused, what are the public protection issues, what types of alternatives. There may be multiple ways that you can treat the water to get to the same level for the desired reuse. And obviously, studies or investigations may be required to determine what would be the most cost-effective solution for a particular municipality. You have to look at what kind of conversions are necessary at the reuse site. Matching supply and demand becomes important. What final uses do you intend to use it for? How much do they need? Do you have more being produced than they can take? Meaning you have to find multiple locations in order to be able to use it all up if you want to eventually get to the point of zero discharge. And how reliable is your overall system going to be? Due to the nature of the interconnection of the water supply and wastewater disposal in our hydrologic cycle, the whole system type planning model is the best approach to try and come up with a solution. In another term, this is called an integrated water resource plan, and it is an iterative process where you identify the type of problem we're dealing with. In this case, if we're looking at having to maybe go to a zero discharge wastewater situation so that you can have to reduce some of the regulatory requirements that you have to deal with. So you formulate objectives in terms of what do you want to do with this wastewater? What information do you have available in terms of potential sites that can reuse this water? What alternatives do you have for treatment? You rank the alternatives, you try and select an alternative to implement, and you investigate some of the economic aspects. Maybe it turns out that your first choice isn't going to be economically viable, so you go back up and start the process all over again with a different treatment alternative. Now, how quickly or easily this engineering process is followed gives you an idea of how quickly a viable solution will present itself. Oftentimes, the ability to come up with the engineering solution can depend upon what type of expertise of the entity seeking the reuse permit. Much of the engineering design data is needed for the permitting process, And some municipalities, the larger ones in particular, may be able to do this work completely internally. A lot of the smaller municipalities, probably not so much. They're going to need an engineering firm or an engineer who would be able to help them work through all of these aspects of the solution. If you lack sufficient expertise to work through those details, DEQ will require an engineer help in the solution. That engineer will need to guarantee that it is workable and does not impact the environment. Now, there's a variety of firms, large and small, that can help the municipality interface with DEQ and help them complete this overall process. The size of the firm that you would employ to do this type of work is irrelevant. Really, it's the expertise of the firm and how they interact with DEQ. Obviously, they want to minimize the amount of time it takes to come up with your solution, and so you want to investigate that engineer and look at them in the context of how do they deal with DEQ and do they have the expertise to actually come up with a solution. Those are going to be key issues. Now, when you look at the selection of the engineering firm, there's a number of factors that you typically would want to consider. Since they're working with you and the public constituents, the engineers need to be able to talk in regular English, no technobabble. They need to be able to communicate with you and with the community at a level that everybody is able to understand what is happening, what needs to happen. You want to select an engineer who can remember to be human. The public will pay more attention and listen to them if they like the selection. You want to pick somebody who's going to be a spokesperson for your process and will be understandable and be able to present things in such a way that the public will buy into your overall project. The engineer has to know what they're talking about and has to be able to be willing to confront any challenge. None of these projects are without difficulties or problems that might crop up during the overall process, and so that engineer has to have the skill and the background to be able to take that new challenge, meet it, and resolve it in the context of solving the overall problem that you're trying to deal with. They also need to be able to talk in such a way that they are spreading the word, keeping everybody informed in terms of what would happen. Some people are never going to accept your particular project. Many of them have their own hidden agenda. These are not the people that you need to worry about. The engineer that you select should be able to work around them to keep the project moving forward. Have the engineer deal with the majority and the municipality itself to get this project moving to a successful conclusion. That does not mean that they are talking above the public. They must talk with the public, and the public in general has to be part of that decision-making process, not just the decision-accepting process. So the engineer, in preparing diagrams, pictures, examples, showing people what you're talking about. A picture is worth 1,000 words. A good picture, a good example from some other location that has implemented exactly this type of project that you're contemplating will be able to show how well it works. That should help keep the public informed in terms of the process and how it's moving forward. A good adage that I've used, and this applies in a lot of different scenarios, is you want an engineer who can leave his or her ego at the door, if necessary, to be able to deal with the project. The engineer's job is to listen and to help get the project successfully done for the benefit of all, not just done his way. He needs to be willing to listen to input, comments, requirements from the public, from the municipality itself, in such a way that he can take that information and provide viable solutions that are to the benefit of the client, not just because he likes to do it that particular way. Throughout the overall process, of course, public attitudes are going to be important. Studies will generally show that a favorable opinion of using reclaimed water for irrigation purposes is a very viable and very useful solution, especially in arid areas, to the wastewater problem. As I mentioned, taking it all the way to the point of using it as a reclaimed water for drinking water has not been so much. I think the first municipality that had tried that back in, I would say, the late 80s, early 90s was the city of Denver. They had a treatment process that took their wastewater to a quality level that was better than any of their existing sources of drinking water, be it wells or be it surface water sources. Over the past couple decades, there have been a number of competitions where reclaimed wastewater treated to that level has actually been entered in water quality contests, and in some points in time they've actually been selected as the best water. So it is possible, but it's still one of those reuses that is not likely to occur anytime real soon. That's probably where it's going to remain at the present time. Management of public perceptions, opinions, typically going to make the difference between success and failure of your particular reuse project. That's kind of the basis of how the overall process needs to lay out. And let me go through a couple of possible examples, case studies, how an effective implementation of water reuse program was taken care of. The first one I want to talk about is in the Irvine Ranch Water District in Orange County, Southern California. This district was formed in 1961. It is a semi-arid area of 12 to 13 inches of rainfall per year, not too dissimilar to parts of Oregon. They had 40% of their drinking water from the Colorado River from Northern California, purchased from the Metro Water District of Southern California, and the remaining 60% came from groundwater wells. They have a distribution system serving about 181 square miles, 600,000 people, 6 cities and unincorporated areas of Orange County. Their first reclamation system was built in 1967. At that time, it had a capacity of about 20.5 million gallons per day, which was 20% of the total supply that was being created at that point in time. At present, they've expanded this capacity to about 28 million gallons per day, and there are over 6,000 customers, irrigation, industries, and so forth. They're hoping to try and reach a peak of about 33 million gallons per day in the next several years. They have 2 completely recycled wastewater treatment plants. Now, the main purpose for this water district has been trying to maximize their water supplies and reducing the demands on their potable sources. At the same time, they're also trying to minimize the amount of treated wastewater that is being sent to a regional agency that will take it into an ocean outfall. Almost all ocean outfalls, people are being told that those need to go away, and so this district is trying to move away from having to send any of their wastewater to that outfall. Currently, they would install the recycled water lines in the ground. At the same time, they would add their drinking water and their sewer lines for new construction, which is not atypical for a lot of areas in the country. At present, they have almost 570 miles of recycled pipelines. What they have found is that it reduces the need to import expensive water to meet irrigation needs. And their existing water supplies have been able to extend to a much higher population without having to look for new resources. The water currently has been set up to meet a tertiary treatment standard, which is typically less than 2 NTU and less than 2.2 per 100 mils of total coliforms. And that's what is the quality of the water that is going to irrigate various crops. They currently use 15 pump stations to distribute this treated wastewater, 12 storage reservoirs, 2 of which are open lakes, and the rest are either concrete or steel tanks. And about 80% of the business and public area landscaping is currently irrigated with this recycled water. That includes all kinds of parks, school grounds, golf courses, cemeteries, and so on. The biggest issue that this district has is with the salinity in the water, because it's a closed loop type of reclamation system. The raw water that comes from the Colorado River is quite saline. It's a very high total dissolved solids. In order to try and deal with that, back in the early 70s, they tried to ban all self-regenerating water softeners that would be part of the communities. That course went to court. In 1997, a court case was brought by the water softener industry. They essentially lost that case, but they're still trying to work to a solution to try and control salinity, because obviously the increased salinity in that water going to the crops means that you are building up a salt intolerance for some of your crops. Seasonal storage is also an issue. Most of their precipitation is in the winter, when they actually are producing more reclaimed water than they can use. Hence the need for the storage facilities to be able to put this treated wastewater to store it till they get into the summer irrigation seasons. They have additional storage expansion projects that are in the works. Finding land for storage has been one of the more difficult aspects of their particular project because of the volumes that they have to deal with. There are some increased maintenance issues compared to drinking water systems. The tanks that they use for storage do have to be cleaned a little more frequently. Your control valves, valve body seats do require a little bit more maintenance than just simply a drinking water system. Any leaks or spills from the system has to be reported to the Water Quality Board. It is still considered a wastewater, not your true potable drinking water, so any kind of a spill is essentially still considered a spill of wastewater. The system has developed a very extensive public education involvement program, all kinds of brochures, videos, workshops, tours, and so forth, to keep the public informed about the project. Their base rate for drinking water is about 68 cents per 100 cubic feet. The current base rate over time has only gone up to about $1.57 per 100 cubic feet. What was about 90% of the base domestic water use rate is now only about 75% of the basic domestic water use rate. So over time, the efficiencies of the system seems like it's increased. It has driven down the overall cost of the treatment system. A second case study to think about occurred in Orange County, Florida, and the city of Orlando. At that point in time, in 1979, a citizens group filed a lawsuit trying to stop all discharge to Shingle Creek, which then flows into a nearby lake. The claim was that the wastewater was impacting the lake and the fish habitat. In this particular situation, a decade later, the citizens actually won the suit. The county had a very limited amount of time, up until 1988, to cease the discharge to the creek. The problem, of course, was in this decade, in the 80s and into the 90s, population growth was requiring expansion of all the wastewater treatment facilities. So the question came up as to what do you do with all this wastewater that you're going to be generating? The engineers looked at 9 different alternatives, and they finally settled on selecting a recycled water to the citrus industry in the area and rapid infiltration basins to essentially recharge the groundwater as the selected solution. Initially, there was very strong resistance to that selected option. The growers in particular were the main adversaries in this situation because they were concerned as to what the effects would be of the reclaimed water for irrigation on their crops. They ultimately agreed to allow the reuse of the wastewater after they had received some research data that basically said it would be beneficial to their crops. And additional money was committed over time for long-term research on the overall effects. So they had some incentives as well as a no-cost supply option for 20 years. They wouldn't have had to start paying for the privilege of reusing the wastewater until most recently. The general public focused on the health and environmental issues relating to the reuse. They did agree, they were kept informed, and they did support the alternative after there were resolutions to address the concerns the city and county adopted to do that. The project became operational in 1986. They had to have it done by 1988, so they were just barely under the wire. They currently produce about 42 million gallons per day of the reclaimed water, with upgrades planned to take it to over 80 million gallons per day. Obviously, these are much larger systems than any of the ones you're likely to see in and around Oregon, but the general concept is still going to be the same. The quality limits that this particular project looked at was secondary treatment with filtration and high-level disinfection. They looked at trying to achieve no detectable fecal coliforms in 75% of their samples in any 30-day period. Fecal coliforms in their general wastewater were typically less than 25 per 100 mils, so the additional disinfection steps pretty well took care of any potential problems from a public health standpoint. The biological oxygen demand was less than 20 and the solids were less than 5, so it was a very high quality effluent in terms of its reuse. 60% of that reclaimed water went for irrigation and the other 40% went to the rapid infiltration basins. The public is permitted access to some of these infiltration basin sites, both to observe and in some cases they've actually been turned into some recreational facilities. At the time, this was the largest reuse project anywhere in the world. It currently irrigates nearly 2,800 acres of citrus annually, and it was the first Florida reuse project to irrigate crops that would be produced for human consumption. It's not a direct application, kind of an indirect, but those citrus crops were the first types of crops that could be used for human consumption. There is a network of pipes anywhere from 6 inches to 54 inches in diameter that directs the water from the treatment plants to the citrus fields. That system could currently handle up to 75 million gallons per day without further expansion. Remember, their goal was to try and achieve upwards of 80 million gallons. Some expansion will be necessary down the road if and when they achieve that capacity. Currently, they're only at about 22 million gallons per day, and 40% of the reclaimed water goes into those rapid infiltration basins. This is about a 200-acre site in terms of the application of the rapid infiltration basins. The project eliminated discharge to the surface waters, which was the overall goal, reduced the demand on the Floridian aquifer, which is where the drinking water for the city of Orlando is coming from. The shallow subsurface Floridian aquifer is recharged due to their infiltration basins and provides additional water for domestic use that probably would not have been there because of the demands that had been on it previously. The long-term research found that citrus, the type of soils that are present there, could tolerate up to 100 inches per year of application, so they could reuse a lot of that wastewater. They saw increased fruit production, growing capacity as a consequence of reusing that wastewater. The trees were bigger, the fruit was bigger compared to adjacent areas where it is not reusing the wastewater. When they looked at the analysis of the wastewater, there was trace amounts of boron and phosphorus, which allowed them to essentially eliminate a fertilizer program. This wastewater reuse had enough of the nutrients necessary that it was allowing the citrus trees to thrive. They did have to be concerned with the soil pH, and does require adding some additional lime at times to keep the soil in a slightly alkaline condition. But the tree condition is as good or better than plants that just use well water as a consequence. So it's a very good long-term solution. Satisfied a lot of people and met a lot of requirements and regulations. In summary then, when you think about a water reuse plan, it is an important element of an integrated water resource utilization and management. You use properly treated effluent, it becomes a water resource, providing many beneficial purposes. There is beginning to be an increased acceptance and reliance on reclaimed water to help mitigate wastewater discharge impacts, and the water reuse can reduce demands upon potable sources of fresh water. In this case, the Oregon DEQ has a well-defined process to promote beneficial reuse of wastewater treatment, and as such, should be viewed as a very reliable resource to help provide the tools and the information that is necessary for any municipality in Oregon to be able to undertake and implement a wastewater reuse program. With that, I want to thank you for your attention. I will be available online if you have any questions that you want to direct to me slightly after this presentation. Thank you.